Okay, going to be doing some additional problems here out of section 7.3, which focuses on a different sort of method for finding volumes. And it's using this method called cylindrical shells. And I talk about this in class a little bit, but I'm going to go ahead and redo it here. The idea is that if you have, let's say, a region that is bounded by two functions, let's say something like this, and you want to take that region and you want to wrap it around, let's say, the y-axis or any vertical line. We'll just do the y-axis for, well, you know what, let's do a general vertical line. Then we do a general vertical line and I want to wrap this way. The problem that we run into if we try the disk method or the washer method is that if I'm going to go this way, I'm going to have a horizontal rectangle, but I can't do that because these aren't functions of x. So, I'm sorry, they aren't functions of y, so I can't do that. So if I try and draw a rectangle in here, the same curve hits on both sides and I can never have that happen. So we are forced in this problem to actually create a vertical rectangle. But with the shells, with the washer method and disk method, this has never been possible for us to do this. So what we do with the shell method is we try and construct a new type of integral or a new formula for wrapping this thing around. So if I take this one slice and wrap it around, then I get this really elongated, what they call a cylindrical shell. So it's this shell that looks like a cylinder. Right, it's a cylinder. It looks almost solid, but it's hollow through the center. And what we have is that the axis of rotation goes through the center here. That's this. So when we wrap that around, we create this. And so the idea is that if we can find the volume of that little shell, then move the rectangle around. Okay, move that rectangle here and here and here, and get all the infinite number of rectangles. Then we will create the entire solid of this being wrapped around. But we have to find the formula for this. So what we do is we cut this thing open, we lay it down flat, and it creates this boxy looking thing when it's laid flat. The width of this is dx. That's the width of this rectangle right here. And then the height of this, from here to here, this distance is just the height of the rectangle. That's the f function minus the g function. So this is going to be f of x minus g of x. And now the last thing to do is to figure out how long this is. But the way we can show that is by thinking about this cylinder being like this. And when we opened it up and laid it flat, the length of this side is actually the circumference of the circle. So it's the circumference of this. So we need to know the radius. We need to know the distance from the axis of rotation to my rectangle. So we come back over here. We're trying to figure out what's the distance from here to the rectangle. And what we do know is that the distance from here to here is the x value, because we're going to let x go back and forth here between, let's say, A and B. So x is going to fluctuate. But we also have this additional amount, whatever this is, and that we would determine by, the given problem and what axis they're asking us to rotate around. If it was just the y-axis, then this radius would be x. But if it's something else, we have to account for that. So I'm going to call this just r for like a radius. And so this side right here would be the circumference of this. Circumference is 2 pi r, so it's 2 pi times the radius. So when we come and create our new formula for integration for using the shell method, we're going to have that the volume of this will be this times that times this. The 2 pi can come out. We have an integral because we're going to add them all up. We're going to go from A to B. And then this radius thing, this radius I can't pull out. It's not a constant. The radius is most likely or always going to contain x in it. So this is some function of x. I'll put r of x here just so you realize that that's a function of x. And then times the f minus the g. and then dx. And that's our new formula for using this method. So let's keep that in mind as we move forward, and I do a couple of examples. So let's take this region. Where is it? There we go. I'm going to do number 3. I'm in section 7.3. So we have y equals the cube root of x, y equals 0, x equals 1, and we want to rotate this about the y-axis. So a quick sketch of this. The cube root of x looks like this. At 0, it's 0. At 1, it's 1. And then way over at 8, it's 2. So it goes like this. Does the same thing this way, like that. That's this one. Y equals 0 is the x-axis. X equals 1, vertical line. And we're rotating this around the y-axis, which is here. So we could do the washer method with this, because I could draw a rectangle this way and have a right function and a left function that always stay the same, but let's try it with the shells. So instead, I'm going to take this region, I'm going to draw a rectangle. That rectangle will be parallel to the axis of rotation. So that's when you know you're doing shells. Everything we've done up to this point, our rectangle was always perpendicular to the axis of rotation. When you use shells, it's going to be parallel. So what I need to do now is try and figure out what the top function is. So the top function here is cube root of x. That's our top function. The bottom function here is 0. And now I just need to find the radius, which is going to be the distance from the axis of rotation to my rectangle, which is just x in this case. And now our limits of integration, we're going to start at x is 0 and stop at x is 1. So this should be a pretty clean setup for this. We're going to have integral, volume is equal to 2 pi, integral from 0 to 1 of the radius, which we said is x, times the f minus g, so the f of x, the top function, minus the bottom function, dx. And then you can just get rid of the 0 and then just multiply those together and then integrate and you're done. All right, let's look at number 5. E to the negative x squared e to the negative x squared y equals 0, x equals 0, x equals 1. Again, we're rotating about the y-axis. All right. So I'm going to draw my picture first. Y is 0 is the x-axis, x is 0 is the y-axis, and then x is 1. E, let's see if this is 1, e to the negative x squared, we looked at that earlier in a different example. Sorry, actually went like this and then like this. Okay, so we're looking at this region here in here. Now I'm using less colors here because we're kind of weaning ourselves away from needing all the different colors. We're rotating around the y-axis here. So my rectangle is going to be vertical, parallel to the axis of rotation. That means I'm using shells. I need a top and a bottom function. The top function here is e to the negative x squared. The bottom function here is 0. I need a radius, which is the distance from the axis of rotation to the rectangle, which here is x, because from x equals 0, the y-axis, to here is x. Also, I need to know what my integral goes from. Starts at 0 on x and ends at 1. That was 1. So that's it. Set it up. Volume is 2 pi integral 0 to 1, the radius, which is x, and then the top function, e to the negative x squared, minus the bottom function, which was 0 dx. Notice there's no squaring of these, right? It's just straightforward, the f minus the g. And then you could do that problem. This is, after the zero's gone, this is just a basic u sub. Let that negative x squared be u. Derivative's right there. You're off by a constant. All right, let's do another one. Okay, I'm going to do number 15. So you have y equals x to the 4th, y equals 0, x equals 1. Rotate this about, x equals 2. So let me draw this. X to the 4th looks like this. Y equals 0, x-axis, x equals 1, it's here. And so we have this region right here. We're rotating it about the line x equals 2. So here's 2. We're going to do a vertical rectangle, which is parallel to the axis of rotation, so I'm using shells. I need a top function and a bottom function, which I have. I have x to the 4th on top. On the bottom, the function is 0. And so all I need now is the radius. The radius is going to be the distance from the axis of rotation to the rectangle, which is this distance. So this is different than what we've done in the past. I'm not calling that x. See, the distance from the y-axis to the rectangle, now that's x. We need the distance from here over. Now, I know the entire distance is 2, so that means that this is 2 minus x. So that's the difference in this problem from what we've seen before. I'm also going to integrate from 0 to 1. So I get volume equals 2 pi integral 0 to 1. The radius is this right here. Put it in parentheses because it's a single factor, 2 minus x times the top function, x to the 4th, minus the bottom function, 0, dx. Multiply it all out, integrate, you're done. Now, what I'm going to do is I'm just going to do one more example of this. I'm going to do this exact same problem, but what I'll do is I'll do it in red. I want to rotate it around a different line instead of this one. Let's rotate it around, let's say x was negative 2. So when I try and find the radius, it's the distance from the axis of rotation to the rectangle right here, right? So what's that distance? Well, it's not x. This distance from here to here is x. The distance from here to here is always 2. So the total distance is going to be 2 plus x. So that's the difference in this. It'll still be the same setup, 2 pi, integral 0 to 1. Instead of 2 minus x, it's 2 plus x. And then the top function minus the bottom, dx. So that's the difference between the two right there. All right, I hope that helps. It's, I'm not doing a whole bunch with this. I just want you to have seen this method. It's pretty useful, especially when you can't write, when you have functions of x that you cannot write as functions of y. Kind of like that when I first tried to illustrate this. All right, I think that's it. I'll stop this video.